just to make it clear why we need to get the mean and why this is considered to be our statistic, meaning our statistic that would be placed in our distribution. Remember that this is a sampling distribution of the sample means. Again, we need to get the means. That's why the statistic is always needed to be a mean. And that's the reason why I need to get the average from the total fat content. Because all the things that you can only place in a sampling distribution of the sample means are means. Remember, this 14% is the mean, right? It says there, the mean, the average, 14%. And this 18.4 is the average of the sample, of one sample, with a sample size of one sample with a sample size of 30. Alright, so 14 and 18.4% are all means. That is part of this sampling distribution of the sample means. Okay, so our next job now is to determine the probability of 18.4 happening. And since we said that the statistic, which is 18.4, is more than the mean, let's get the probability of 18.4 happening and values that is above it happening. So for us to determine the probability of 18.4 happening, we need to grab our Excel and we need to code for the cumulative distribution function given the mean and given this standard deviation. Alright, let me grab Excel and let's find out. And this is my Excel, and you have seen this before. I'm just going to edit some values. We know that the mean of the sampling distribution was 14. Okay, and the standard deviation itself of the sampling means was, let me check, 5.48, 5.48. And for us to, so now that we supply that, we need to give values for the cumulative distribution function. And remember that the way to do this, I've shown this on the last video, but I'm going to say it again, is you need to supply for the x values, for the mean, for the standard deviation, and to indicate whether you wanted a cumulative. Since you wanted a cumulative, I said true. Alright, I hope that's clear. Now you see that my value of x is quite big. The standard deviation, the mean is only 14. So if I go back to my drawing, you understand that if this is 14, then the values right here maybe would be around 8. So let's start at 8 and let's end maybe at 20. So let's start at 8, let's end at 20. So let me grab my Excel back again. So I said let's start at 8, maybe let's do an increment of 8.1, and I will just double click on this, and now we have some values. Alright, that is quite nice. Oh, I forgot, the standard deviation is actually 5.48, so it means that we need to actually still go further away. So let's start at a 1. Alright, start at 1 and 1.1. And let me double click on that again. See what we get. I think my increment is quite small. I will do a 0.5 increment on this. Alright, that is nice. So the result of that increment is this cumulative distribution function, and the graph of that I would show it to you. And you've seen this before, so it's not surprising that it looks like a sigmoidal curve right there. So that's the graph, and the probability that we wanted to determine is 18.4. So let's find where 18.4 is. Should be around here. Alright, there you go, 18.4. The probability of getting 18.5, so we can just use 18.5 because this is 18. Let's use 18.5 is 0.794. all right, let's write that down. 0.794. remember that the cumulative distribution function is not getting this. It's actually getting from the negative infinity to a value. So it said that the probability of getting this is 0.794. It means that the probability of getting a value more than 18.4 is 1 minus 0.794, and hence the probability of a value 18.4% or more happening is that if with using a calculator, let's say 1 minus 0.794 is around 20%. That's 20%. Let's write it on a different color so we can see. So the probability is around 20%. 20%. And quite obvious that since 18.4 is right here in this corner, that indeed is 20%, and that's a large percentage. Now, for you to determine whether you're going to reject or accept the null hypothesis is for you to set a value, like how small would the probability be before you can say that a certain statistic shouldn't happen but it happened. In this case it's 20%. That's quite large, so we expect it to happen. And when you test a certain sample, 20% is quite large, so it's okay, it does happen, and we can say that alright, it's 20%, so it does belong on that distribution. But before I continue the analysis, I first need to talk about my decision making probability, which is usually like 5%. So if a certain value falls at 5% or lower than 5%, and if it happens, that's kind of weird, and we would say that it doesn't belong on that probability. But if it's more than 5%, we expect it to happen, and hence it belongs on that probability. And if it's less than 5%, we reject the null. If it's more than, other way around, right, if it's less than 5% and it still happened, it means that it doesn't belong on that probability and we reject the null. And if it's more than 5% and we expect it to happen and it did happen because we took a sample and the sample said that it happened, then we accept the null. And in this case, our null was no effect. And so our conclusion is the beer houses and the steak houses did not statistically give a significant increase in the fat content of men.